Okay, good morning. So let us continue our lesson with vectors. Uh, Before starting the last part of vectors, I want to give you an example. Let us see how it works, okay? Uh, so let me change the color here. So my question is this. If I have any triangle that you like, for example, this triangle, this is my triangle, and then let me call it ABC. I go and find the midpoint of line segment BC. Okay, so for example, if I can find it more or less properly, this would be somewhere here. So assume that M is the midpoint. So M is the midpoint of BC. And then I don't know if you remember or not, if we have a line segment which connects A to M, this is called a median of the triangle. Yes, so let me just draw that median. Yes, so this is the median. What I want to, so AM is called a median. Yes, what we want to show this, there is no vectors involved in this problem, but I want to write a vector or a vector expression here. I want to show that the vector AM is equal to the average of the vectors AB and AC. In principle, I want to show that vector AM is 1/2 of vector AB plus vector AC. Okay, this we want to show. Okay, so is that clear? So it means that, of course, I told you that this is a triangle. No vectors is involved. I take the midpoint here and I connect this A to M, and then I want to show that vector AM is equal to vector AB plus vector AC multiplied by 1/2. Yes, how we can prove this? But be careful, let me ask you one question here. For example, I will write and clean it. For example, if I give you this is 5 centimeters, if I give you this is 7 centimeters, do you think this theorem means that the length of AM is 5 plus 7 divided by 2? So that's also something I want you to know, yes? Okay, so let me clean this for the time being, don't distract you, and say, just think about this problem. I want to show that vector AM is the average between these two vectors. Yes, it means that if I add these two vectors and then multiply the vector by 1/2, I will get exactly the vector AM. Any ideas? Yes?
I just thought if you parallel transport AC to AB,
Mm-hmm.
you add them first, and then you draw the AC. Like, yeah,
Your idea is good actually, but it's not possible to prove it exactly, yes? Is that so I exactly understand what you mean. You are saying that I will take this one because I want to add AB to AC. So I will take this one as a vector, parallel transported from here, and then I add this vector to that vector. Definitely this becomes this vector. This is clear. But the claim is that, yes, you are right. This new vector is 2 times larger than the median vector. Okay? But we need to prove it exactly. Yes, that's the point. But I want you to get used to how to work with vector algebra. You see, the way that I think about this problem is not that geometrical. Of course, geometry is also involved. I want to use algebra somehow, algebra of vectors to solve this problem. I would say that, okay, I want to connect a relation. I want to establish a relation between the vector AM on the left and vectors AB and AC on the right. Okay, so if you don't mind, let me just draw this as vectors for the time being. So this is my vector AB, this is my vector AM, and this is my vector AC. Okay, so in this triangle that you see here, I can write a relation for AM and AB. Yes, can you tell me, for example, let me write in triangle ABM, what can I write? I can write that a vector AM is equal to what? Is equal to vector AB plus vector BM. Do you agree? If I add these two vectors, it becomes exactly vector AM. Is that clear for everyone? Yes. So I would write that AM is equal to AB plus vector BM. I would say that this is a good starting point. Why? Because I am establishing a relation between my vector AM on the left and one of these vectors on the right. Of course, I have some extra component appearing in the problem, but that is inevitable. So let us take care of this later. And then, do you think, what should I do? What do you think? Yes?
Do the same thing, but say that
Yes, in this triangle, yes. I will do the same thing, yes. So I would say that in triangle, I don't know why. So let me take this. So in triangle ACM, what can I write? I can write AM is equal to, if I add vector AC, but this time to vector CM, it will generate for me the same vector AM. So it becomes AC plus CM. For these two relations, even I don't need to look at the picture. Yes, this is the Schall equality here and the Schall equality here, because B's are the same, so they are cancelled, so I have AM, and here C's are the same, they are cancelled, so that's AM. So you can write this relation either using the Schall rule, or you can just look at the picture. Yes? And then what is the next step? What would be the next step, do you think? That's also a good relation, because I have AM, which is on the left, is connected somehow to AC, which is exactly on the right, but of course with some extra piece of component that we don't need. So what can I do? I can start adding them side by side, yes? I would say that on the left-hand side, I have AM plus AM. I don't know what is happening with this iPad. So AM plus AM is equal to. So on the left-hand side, on the right-hand side, I will add AB plus BM. Yes, let me write all the details. You don't need to write all the details, of course, here. AC plus CM, yes? Is that understandable? So I had two equalities. I add them side by side. I will get this relation. But then, you know that addition of vectors is commutative and associative. So it means that if I want to, I can put them next to each other and put these two next to each other, yes? On the other hand, on the left-hand side, AM plus AM has a better name. What that name is? It's 2AM, yes? We just learned about multiplying a vector by a number. On the right-hand side, I will write AB plus AC, and then I will have plus BM plus CM. Okay? In this expression, can I use Schall's relation here? Yes or no? Be careful. Yes or no? No. even though m is in common, but m is not the middle letter. Yes, so this is not a shell combination, so I cannot use the shell combination. Then I have to refer to my picture. What is bm? Bm is this vector. Yes, what is cm? Cm is this vector. These two vectors both lie on the same line. They are of the same size. Why? Because I told you that m is the middle point. So the length of bm and the length of cm are exactly the same. But as you see, bm points to the right and cm points to the left. So these two vectors are opposite vectors. Yes? So this vector is actually the zero vector here. But I know that if I add the zero vector to any vector, the result is the same. So it becomes 2 vector am is equal to ab plus ac. And then what I need is I multiply everything by 1/2. The left-hand side becomes am. The right-hand side becomes 1/2 ab plus ac. So that's a very nice relation. Sometimes the people who are going to join mathematics competitions, it's good to know these relations. Of course, if we continue our lessons, we will actually cover all these things. So vector algebra is actually a very important tool in your hand. Okay, now let me go back to my question. Assume that I tell you that this is 5 centimeters, and I give you this one is 7 centimeters. Do you think that I can use this relation that I have proven I just proved now to calculate the length of the median AM by adding 5 to 7 and divided by 2? So in other words, do you think that I can say that the length here is 6 because 5 plus 7 multiplied by 1/2 is 6? Can I conclude based on this fact that the length of AM is 6? This is not true, yes? So be careful. This equation is a vector equation, is not something between the lengths. So what can I say at most? Let me change my color. This is not part of the solution. When you say that AM is equal to 1/2 AB plus AC, at most, if you want to say something about the length of the vectors, you would say the length of the vector on the left should be equal to the length of the vector on the right. This is what at most I can say. Yes? But do you remember the length of a number multiplied by a vector? Here 1/2 is positive, so it becomes 1/2 of the length of vector AB plus vector AC. Yes? But this is not equal. This is important. This is not equal to saying that 1/2 the length of the first vector plus the length of the second vector. Yes, this is not true. Yes, do you remember? Because up to here, all the calculations are correct. But from here, I cannot go to this one. And so it means that if you tell me that the length of AB is 5, if you tell me that the length of AC is 7, if I add them and I divide it by 2, I get, of course, 6, but this is not equal to the length of AM. Yes? Is that clear? So be careful. This is just a vector equality, not an equality between lengths of the vectors. Yes? This is crucial to appreciate. So do you remember why is that? We discussed about this before, yes? That is the triangle inequality. If I have two vectors u and v, if I add them and then measure the length, it is not in general equal to the length of the first one plus the length of the second one. Do you remember what was the sign that we can put here? That was not equality. What was that? Yes?
Smaller. The right one is bigger.
Yes, not bigger, equal, yes. So this becomes less than or equal. So that was called the triangle inequality, yes. This I want you to remember. That's a good thing to know. So, okay. Any questions here? Okay, let me give you another example. So I would say let O, A, B, and C be points such that you have 2 times OA vector plus 3 times OB vector is equal to 5 times OC vector. So there are four points, O, A, B, and C. We don't know about the exact location of these points, but we know that this relation is established between these 4 points. The claim is that we want to show that A, B, and C lie on the same straight line. Yes, show that A, B, and C lie on the same straight line. Okay. That's also a good question. This is at the level of your knowledge about vectors in principle, but that would be probably a harder question. So first of all, let me tell you something. If I have 2 points are always guaranteed to be on the same straight line. Yes, if I have 2 points, definitely I can put my ruler next to them and draw this line. If I have these 2 points, then I can do the same thing with these 2 points. So always 2 points lie on the same line. That is clear. But there is no guarantee that if I have 3 points, they also lie on the same straight line. It might be true or might be false. Yes. For example, if I can draw it perfectly, more or less precisely, these 3 points are on the same line, but these 3 points, there is no way that they are on the same line. Yes, because the line containing these 2 is this one. The line containing these 2 is only this one. The line containing these 2 is only this one, and they do not lie on the same line. So it is not trivial. If I give you only 2 points, nothing needed to be proven. 2 points are they always lie on the same line. But when it comes to 3 points, it might be true or might be false. This problem claims that if this relation is established between these 4 points, then it is guaranteed that point A, point B, and point C lie on the same straight line. Do you have any idea how to show that? Because this problem, you cannot draw any a very nice picture here because you don't know anything about where O, A, B, and C are. They are just random 4 points on a space, in the space, but of course we have this relation between them. Do you have any ideas? This is also a good problem. I want you to. Unfortunately, on iPad, I don't know, we don't have the pausing option. It's very strange. You cannot pause the video and then, if I stop the video, I don't know if you know how to do it, please let me know because I really need that. If I stop recording and I start recording again, it would be a separate file. Yeah. Yeah, of course, probably they want to do it that you have to buy another application. Otherwise, I don't think it is hard for Apple to design a pausing button. Yes. Yeah.
But you can stop
Yes, that means that it needs more work for me. Yeah, I know that I can do that. Yes, please. Can you speak louder? The same screen recording on the iPad. I'm not using any kind of application. Okay, so I want to give you a hint. Okay, this problem is one of those problems that you have to be patient to see why this method that I'm offering will work. I want to tell you that instead of 5, write 2 plus 3. Okay, so you might say that why this is useful, but you need to be patient and see why this is useful. We do that and we do some algebra to see we can conclude this point from here. So, okay, I would say that I told you that this is not clear from the beginning. This is one of those problems that after being solved, you get some experience about that, yes? So instead of 5, I write 2 plus 3 OC. Okay, now I want to ask about your intuition. So what would be the next step, do you think? Just to think naturally. Yes, Afsha? Yes, distribution is probably, yes, a good natural step to do. So it becomes 2OA and plus 3OB. This becomes 2 times OC plus 3 times OC again. Okay, that is natural. It was not clear why I have written 2 plus 3. Of course, instead of 5, I could also write 4 plus 1. I could also write 6 plus minus 1. Why I have chosen to write 2 plus 3 uh, is somehow clear because 2 plus 3 appears on the left-hand side as well. Probably, if I want to break 5 to 2 pieces, 2 plus 3 is a better choice. Yes? Okay, then what? What is your intuition? How to continue? If you just want to think naturally, why do you think I divided 5 to 2 and 3? Yes, Ali? No, be careful. So if you mean that I can remove these 2 with that 2, this 3 with that 3, no. But if I had 2A only to this one, this, yes, here, 2OA equals to 2OC, in that case, I can remove. But no, I cannot say I can remove this one with that one and this one with that one. I can either divide by 2, then this will cancel, this becomes 3 half, this will be cancelled, this becomes 3 half. This is possible. Or I can divide by 3, then it becomes 2 over 3, this will be cancelled, this becomes 2 over 3, this will be cancelled. Yes, I cannot to choose divide one of them by 2, the other one by 3. Yes, this is not possible. Ideas? Yes?
Maybe you want to get as few variables as possible.
Okay, how? I'm asking you what would be the natural next step. I don't know if that is natural or what. Might be I have worked with these problems so much, so this seems natural for me, but yes, Rasmus?
Somehow show that.
No, the algebra is not finished. This is my guide.
Yeah,
We need to continue with
yeah,
algebra.
but somehow show that somehow OA is equal to OC, but with a little part missing, where OB is slightly bigger than OC.
Okay, intuitively might be that's correct, but
Yeah, it's
make
not very
this,
mathematical.
yeah.
I don't really know how.
So just say something at least. Do you really ran out of ideas? Yes? Yes. Yeah. So I just mean that's natural, yes. So what I do, for example, I see that there is a factor of 2 for this one and this one, and there is a factor of 3 for this one and that one. For example, let me move this to the left and let me move this to the right. Yes, let us do that. So you need to also follow your instinct sometimes. So 2OA minus 2OC is equal to 3OC minus 3OB. Is that right? But what is the next step then? It's very natural now. What do you mean by simplify? Yes?
We could
Factor out, yes. Why do you hesitate to say that? So you have 2OA minus 2OC. So might be it's a good idea to write this. Okay? Now I want to tell me something about this. Can I write this more compactly using vector, what you learned about vectors? OA minus OC vectors. What can I write instead of this? Is famous. You need to know that, yes?
We should be able to write as OA minus CO, or no, plus CO.
CO, yes. So let me just follow you. So it becomes 2 OA. Instead of minus OC, I hope everyone agrees that I can write plus CO. Is that right? Yes? Everyone agrees? Because I was able to interchange these two and write them. On the right-hand side, what can I do? The same idea probably will work, yes? I can write OC plus BO. Are these shall equalities or not?
Yes.
Not in this form, but yes, you are right. So I would write CO on the left and OA on the right. On this one, I would write BO on the left and OC on the right. Yes? Now what can I write? I can write 2. What can I write instead of CO plus OA? CA. And then what can I write here? BC. Okay. But, so you see, I am just doing algebra. I'm not imagining any pictures or something. So I have started from this algebraic relation, and I have written this one for you. Now the point is that I want to do something, and then I want to ask your opinion about that. I want to divide by 2. You might think why this is good. Let us be patient. So CA becomes 3/2 of BC. Yes. So this is what we got by just algebra of vectors, nothing more. Yes. Let me make it more right. Okay, but then I am claiming, I want to ask you why. The problem finishes here with just one sentence of argument. Why is that? What was the goal? The goal was to show A, B, and C lie on the same straight line. We got this one, and I am claiming that from this relation, I can conclude what I want. But of course, I have to explain it in my solution. Why? From here, my claim is that we can conclude how A, B, and C are on the same straight line. A straight line, yes. Why? Why? Pardon? Yes, why?
If CA, if BC, if the line BC is 3/2 of
Mm-hmm.
line CA,
Mm-hmm.
then I mean, no.
Yes?
We can at least conclude that BC and CA are parallel.
This is that's it. This is very important. I told you yesterday. If two vectors are parallel, not yesterday, the previous session. If two vectors are parallel, do you remember I told you that? This is a very important remark. Let me write it again here for you. Okay, so two vectors are parallel, two non-zero vectors, of course, two non-zero vectors are parallel if and only if. Do you remember I wrote IFF and I said that this is not a misprint, it means if and only if one of them, each of them, yes, each of them is a multiple of the other one. This is extremely important, okay? So what does it mean? It means that if you know that two vectors are parallel, then you can conclude one of them is a multiple of the other one. On the other hand, if one of them is a multiple of the other one, then it means that you can conclude that these two vectors are parallel. Yes?
And then it's obvious that they're on the same line because one starts from one ends with C and one begins with
Exactly.
C.
That's exactly. So what Rasmus mentioned, according to this remark, we can conclude that vector CA is indeed parallel to vector BC. Why? Because one of these vectors is a multiple of the other vector. So this conclusion is valid. But then look, as Oscar mentioned, these two vectors are on the one hand parallel, on the other hand they share a point. So they have to be on the same straight line. Yes? So why is that? For example, if this is vector CA, and where is vector BC? BC is something like, so this C is the same C. So for example, this is vector BC. If this situation happens, and if A, B, and C are not on the same straight line, this cannot happen. Yes? Because CA and BC are parallel, and they share a common point. Do you understand what it means? So I have two, I don't know, I have this one and this one. I want to make my finger parallel to this pen, keeping this point. Yes? So I have to put them in the same straight line. So then it means that since CA and BC have C in common, it's better, have the point C in common, and are parallel, we can conclude that they are on the same straight line. Okay, so that's also one problem I want you to know about. Okay, any questions? Yes?
Can you explain again how you know that they're parallel?
So do you remember what was the definition of multiplying a vector by a number?
Yes.
So, okay, so if you multiply a vector by a number, it generates a new vector which is parallel to the old one. Yes? So it means that if I take this vector BC and I multiply it by 3/2, it becomes a new vector which is parallel to BC. Yes? On the one hand. On the other hand, CA is equal to this vector. So CA, which is a multiple of BC, should remain parallel to BC. Is that understandable? Yes, so it means that this is very important that you immediately can conclude this. If you see that a vector is a number multiplied by another vector, you can immediately conclude that these two vectors are parallel. Yes? And vice versa. If two vectors are parallel, then you can conclude that each one of them is a multiple of the other one. That is extremely important to realize when you are dealing with vectors. Any questions? Is that understandable? Okay, now the last part of lesson is actually we want to use the power of algebra to work with vectors. Yes, so it means that somehow in algebra, what is important for us are numbers. Yes, so here vector is a geometrical shape. It's an arrow or something. But now we want to encode the information in the vector by numbers. And then I want to stick to the vectors in the plane, on the plane. Yes, not in the space, because there we need 3 dimensions. So assume that we only work on the piece of paper and we draw all the vectors on a piece of paper. So we are working on a plane, yes? Okay, so how many pieces of information a vector gives you as a geometrical object? So if you draw a vector in a plane, it gives you 2 pieces of information, magnitude and direction, yes? So from geometrical point of view, any vector encodes 2 pieces of information, some number, which is the magnitude, some number, which is the direction. Now we want to do a vector algebraically, okay? So it means that if I want to represent a vector with numbers, one number is not enough, because one number is just one single piece of information. But there are 2 pieces of information encoded in each vector, yes? So it means that I need to have 2 numbers to be able to talk about a vector. So let me go to GeoGebra. So here, let me draw a vector for you here. So I go here, I point here, for example, to this vector. So that's a vector. How do you think it is a good idea to encode this vector by numbers? Of course, this is already done in GeoGebra, yes? You see that on the left column, this vector is written for a column 4, 4, yes, or 4 and 4, yes? So let me draw another vector for you. For example, this vector. So what are the numbers you see in GeoGebra? 6 and 2. How do you interpret 6 and 2? How do you interpret 4 and 4? Anyone else? Yes?
4 is 4 steps.
Uh-huh.
To right and then 4 steps up.
4 steps drop. What about 6 and 2?
6 steps to the
Right, 2 steps up. Is that right? Now let me ask your understanding. If I put a point here and a point here, and if I draw a vector from the point E to the point F, what do you think would be the numbers for this vector? From E to F. Yes, Tim? 1, 2, 3, 4, 5, 6, 7 to the right. So it would be 7. And how many down? -2. So that is very easy. So from now on, if you want to encode a vector with numbers, you need 2 numbers. One number tells you how much you need to go to right or to the left. If you go to the right, you have a positive number representing that movement. If you go to the left, you have a negative number representing that one. And if you go up, it's a positive number, another positive number, and if you go down, a negative number, yes? So then let us see if this prediction is correct. So you see, as you predicted, the GeoGebra, of course, GeoGebra provides this beneath each other, but in your book it is horizontal. So so I don't know if I have the pen here as well. So for example, for this vector, we write 7 and -2 in the book. Okay, this is a little bit unfortunate as well, because people might get confused. Do you know that 7 minus 2 might refer to what? Might refer to one single point whose x coordinate is 7 and its y coordinate is -2. So this is why GeoGebra is avoiding this notation. But this is actually very common. Not that is a mistake in your book. This is very, very common. Yes, Rasmus?
Why is that unfortunate? I mean, that's like, aside from vectors being directions, they're also super useful because they can tell you a position. So
yes, they can tell you a position if you draw them from the origin.
Yeah. But
Yes,
so-
in that
so-
case, the tip of the arrow has the same coordinate as the components of the vector.
Yeah, so then why is the problem that you write it the same as a position?
I don't like it myself, so I don't have any objections about your point of view. But when in mathematics, so if I just write 7 and minus 2 and just leave the classroom, when you come in, how do you interpret? You can interpret it in two ways, yes? You can interpret it as one single point, or you can interpret it as an extended object called vector, whose initial point is the origin and is the tip of the arrow is at that point. Okay, but if you write it as column as GeoGebra does, there is no matter of confusion. So if you write it in that way, of course there is also a deeper reason that we write it like that. This is a column matrix. Later might be you study. That's called the column matrix. Yes.
There's no origin in this notation, so how can we even know this is a vector?
That's a convention. So that's what I'm saying. So if I just write 7 and minus 2 on the board and leave the classroom, and the next teacher comes in, they don't know if I am talking about coordinate system or I am talking about the vectors. Yes? Yes, Rasmus?
Sorry, but I mean, isn't just like when you write a number or scalar value,
Yes?
you don't need to like. Or yeah, I guess that's why you have units, but it's not like we write numbers fundamentally different or like lay them out in a different way when we're talking about temperatures or when we're talking about distances.
Yes?
Talking about lengths or talking about time. We still write them as same numbers, just as vectors can be a direction or a point or a bunch of other things in physics or whatever. Then it feels like, I mean, yeah, of course you can't know if they're talking about a direction or a point if we just write that in a horizontal way. But just as
Now what I'm saying is that a point and a vector are different geometrical objects, aren't they?
yeah,
Yes?
that's true.
But if you say that there is a connection between the notion of a point and the notion of a vector, I agree with that. But using the same symbol or the same notation for two different geometrical objects needs at least an explanation. Yes? Yeah. So it means that if I am talking about vectors, I know how to interpret them. And if I am talking about the points, I know how to interpret them. Yes?
Can that be written and that can be a vector without establishing an origin point? Like can you write that as a notation for vector?
Yes.
Without an origin point?
Yes. And in that case, it means that the starting point and the final point are not relevant. The starting point is not relevant. So for example, if this vector AB is 4, 4, I can have this vector from 1, 2, 3, 4, 1, 2, 3, 4, yes, from here to here as well. So you see, in GeoGebra, these two, by the way, are these two vectors different vectors or are the same vectors? The same vectors because of the definition. Of course, I can see the difference. One of them starts from point A, one of them starts from point G. The locations are different, so we can recognize the difference between these two. But according to our definition, vector GH and vector AB are mathematically by definition equal. If they are by definition equal, and then you see in GeoGebra, if you go down there, the column vector for this new vector A is 4, 4. The column vector for the previous vector is still 4, 4. And this is not inconsistency, that is good. Because if two vectors are the same, we expect that the numbers representing them should be exactly the same. Otherwise, we have inconsistencies, yes? So what you say is exactly what we interpret. So if I see 7 and minus 2, if I see this, yes, oops, if I see this, it doesn't matter where I start. It matters that I have to go 7 units to the right, 2 units down. That would be the vector. And of course, if you start from the origin, there is a name for that vector. That is called, as you said, the position vector. That's it. If I start, for example, let me consider this one. So I start from the origin. I go 7 units to the right, 2 units down. So I will go from here to here. This vector is the same vector. So this vector ij is exactly the same vector. This vector ij is exactly the same vector as ef. Okay? But for this ij, I call it the position vector. The position vector of which point? Of point j. Yes? Now, if I ask you, what are the coordinates of point j? What are the coordinates of point j? Yes? 7 and minus 2. So that is the only case. So you see, if I draw the vector from the origin, the point, the final point, has the same numbers as the vector. Yes? Be careful. If I consider there are two different names, 7 and minus 2 are called the coordinates of j. But here, if I am referring to a vector, 7 and minus 2 are not called the coordinates, are called the components of the vector, EF. Yes? So please appreciate the difference between these two words. So if you are referring to disordered numbers for coordinates, for a point, you call them coordinates. But if you are referring those numbers for the vector, you call them components of a vector, not coordinates of the vector. Yes? Is that clear? Okay. Now, what is the benefit? Now we want to have a dictionary to translate geometrical operations into algebraic operations and vice versa. So can you tell me what will happen if so now let me go back to my notes here. So we learned that from now on, if I have a vector, I would write equal, by the way. I don't know. Yes, your book is also using, that's good. So if I write a vector, I write A and B. Okay, so when I want to use a vector, I put this equality. And if I want to write a point, I just write a point A with coordinates A and B. So that's also another difference, how you need to use these things. So here, these are called components. I write this equality if I want to mention a vector. But here I call them coordinates, and if that's a point, I don't put any equality between A and that pair, yes? So these are the things that we want to use. Now my question is that, if I give you two vectors u and v, I told you how to add them. So you can use the triangle method or whatever. Now, in this new system, a vector is not an arrow, is an ordered pair of numbers. So let me call them A and B. If I have another vector v in this new setup, that is also an ordered pair. Call it C and D. Now, what can I do if I want to have u and v added? Okay? So this becomes a new vector. We already know that if I add two vectors, it becomes a new vector. And in this setup, a new vector it means a new ordered pair. Now my question is that how the ordered pair of this vector connects itself to these two ordered pairs. Yes? Yes, that's exactly the same thing. Yes? So that is, you see, the algebra is extremely simple now. Instead of drawing pictures, I just add numbers, as simple as that. So I can do all the calculations for algebra, for vectors, using very simple algebra. So that is the case. So u plus v becomes a plus c and b plus d. Yes? So it means that I add these component wise. This component with its corresponding component, this component with this one. Is it natural, by the way? Because I cannot define this. I have already defined that for you. Okay. For example, I have u equals to 1 and 2. And then v, it is, for example, 2 and 3. What is u plus v? It is 3 and 5. So let us understand this algebra. This tells you that this vector takes you 1 unit to the right. Yes? This vector takes you 2 units to the right. If I add them together based on addition of vectors, how many units I will go to the right by the sum of these two vectors? It is clear I go 3 units to the right. Yes? So remember these two vectors. Let me go to GeoGebra and draw them. So 1 and 2, 2 and 3, yes? So let me go to GeoGebra here. Let me try to move this a little bit higher. So I want to draw a vector 1 and 2. So I go 1 unit to the right, 2 units up. This is my vector. This vector is 1 and 2, yes? And then I want the vector 2 and 3. 2 and 3, for example, from here. I go 2 units to the right, 3 units up. Do you agree? So this is the vector the first one was the vector 1 and 2, the second one was the vector this one. Now I want to add these two vectors according to addition of vectors. Do you remember what I'm supposed to do? I am supposed to parallel transport this vector from the tip of the first vector, and there is an option in GeoGebra. You go and use this one, okay, and then you click here and click on your vector. So that is the parallel transport of your vector. Yes, is that clear? So I parallel transport this vector to this end of this vector. And then what I'm supposed to do, I go here and draw the new vector. So this is the new vector. Yes? And now let us consider how many units I go to the right by this new vector. 1, 2, 3 units to the right, and 1, 2, 3, 4, 5 units up. So it is very clear. So if I add vectors, I am adding the components. So you see that the algebra is actually very simple now. So if we go back, from now on, if I have u equals to a, b, and c and d for v, then if you want to add them, simply add them component-wise, a plus c, b plus d. Yes, if you want to subtract them, you should be able to convince yourself that the same is true for subtraction. And if I have a number, so let me call this number a Greek letter, so that's not confused with the component. So let me call it lambda. Lambda is a number. Yes. If I multiply lambda by vector u, what do you predict? What will happen? If I multiply a vector, so for example, let us take this vector and ask you multiply it by 5. What do you think will happen? Yes, Rasmus?
We would multiply the components by the scalar.
By the same number. Is that understandable? Yes, because this takes you 2 units to the right. And now I want to multiply it by 5. So it means that I have to add that vector by itself 5 times. So I will move to the right 10 units, 5 times. So that's also correct. So this becomes what? Lambda times A, lambda times B. So that is extremely important to remember. So I want you to understand the deeper concept here. So what we are doing, we are establishing a relation between a geometrical object, which is a vector, and algebra. So instead of drawing pictures, we are doing numbers. Yes? Adding numbers, subtracting numbers, multiplying numbers, and that's easy. One more question that I want to ask is that how can I find the norm of the vector? How can I find the length of the vector? I want to generate a formula for finding the length of the vector. If I give you these two components, what would be the length of vector u? Yes? Yes, Ali? Pythagoras theorem, yes? So, because if I go to GeoGebra here, for example, if I ask you, can you tell me the length of this vector AB here on this picture? Can you give me the length? You would say yes. I will consider this line and that line, and then this becomes 90 degrees. So I will use the Pythagoras theorem to find that. Is that clear? But what is this length? This length is exactly equal to the positive part of the x component of u. And this is the positive part of the y component of u. Yes? So now, if you understand what is going on, can you tell me how should I write a formula here? So if u is this vector with components a and b, then norm of u is equal to, can you write a formula for me? Yes?
Norm of a plus, is it norm of a to the 2 times norm of b to the 2?
Times?
No, plus.
Plus. You don't need to say norm. Norm, by the way, that's not a good name for numbers. Norm of a means absolute value of a, but even we don't need absolute value here. Why? Because we raise it to power 2. So we don't need to be careful about that. So this becomes exactly what you said is correct. It becomes the square root of a squared plus b squared. That's also something that I want you to know. Yes? Is that clear? Now let me give you an example here. This example is important, okay? So I would say consider vectors u with components -1 and 3 and v with components 2 and -5. Determine the exact length of the vector, I don't know, 2 times u minus 3 times v. We want to find the exact length of this vector. Okay, can you guide me through this? What should I do? I have given you 2 vectors in component form, algebraic form, and I want you to determine the exact length of this vector. So what should I do first? Yes, Ali? And so you mean I am supposed to find the components of this vector first? Yes. So what I'm supposed to do, so I will go here. I would say 2u minus 3v is equal to 2 times, instead of u, I write its components, -1 and 3, and then I have -3, instead of v, I write its components. So what happens? I multiply 2 inside according to the rule that I learned. It becomes -2 and 6. I multiply 3 inside. It becomes 6 and -15. And then I subtract them component-wise, meaning -2 minus 6, meaning 6 minus -15. Yes? So then it becomes -8 and 21. Yes? So this means that 2u minus 3v is equal to -8 and 21. Now the question is that the question mark is the norm of this vector. So what should I do? According to the formula, I should take the square root and write -8 to the 2 plus 21 to the 2. Yes? So -8 to the 2 is what? 64. And that one is 441, yes? And then what happens here? This becomes how much? 505. Yes? Yes, so that is exact value. I don't want to simplify this more than that, unless that's an exact complete square, which is not. So the question mark is this one. It is square root of 505 length unit. Yes, is that understandable? Okay, so that is the calculation that I want you to learn. There is only one thing left, and the lesson will end here. And that is the standard unit vectors for the x and y axis. Yes. So if you have the x and y coordinates, so let me try to draw this here. And this one. Assume that this is 1 here, and this is 1 here. If you have this vector, there is a special name for this vector. This is called the unit vector corresponding to the x-axis. This is my x-axis. This is my y-axis. This vector that I draw from the origin to this point 1, of course, this is a unit vector. Why? Because its length is equal to 1 unit. The origin is the initial point, and this point is the final point. There is a name for this one. In the book, I see that they show this one with this symbol. This is called the unit vector. So you write E, and then you put an index X below it. And in principle, it is printed in bold letters, but usually we put a hat on it. Do you remember I told you that if your vector is a unit vector, instead of putting an arrow, you usually put that hat symbol on that. So that's if you want to write with the handwriting, it is hard to print it in bold. But in the book, it is printed in bold, okay? So this is EX. Another symbol that is very common is I with a hat. For some reason, your book has chosen this notation for this vector, but in physics books, usually you have this symbol. It doesn't matter. So both of them are referring to the same thing. And if I do the same thing for the y here, the y-axis, this is called E sub y, or it is called J vector. So this vector here is E y, or people usually call it J. These are the same symbols that we use. Here we have EX, or we can call it I. Now, can you tell me what are the components of EX? What are the components of EX and EY? So EX, how many units EX will take you to the right? 1. How many it takes you up or down? 0. So you remember, the components of this unit vector is 1 and 0. The components of this vector is 0 and 1. And then if I have any vector, so if I have any vector here, for example, this vector, every vector can be decomposed as 2 vectors in terms of EX and EY. So in principle, if my vector has coordinates A and B, then it is important to realize that V can be expressed in terms of EX and EY by multiplying EX by A and multiplying EY by B and adding these together. That's also a good relation to remember. So any vector can be written in terms of these unit vectors AX, EX, and EY. So if I want to write it here, I would say that if V is equal to A and B, if and only if V is equal to the first number multiplied by EX plus the second number multiplied by EY. that is also good to know, that every vector can be written in terms of these two unit vectors. Okay, so I think whatever we wanted to cover about vectors is finished here. Okay, I will update the Google Classroom so that which pages you are supposed to work on and study on yourself. You have still a little bit of time, so let me update that. And I will also put these notes on Google Classroom later, okay? Thank you.